Hey everybody, thank you for joining us. Let's wait a couple of seconds to let more people join. Um, Today we will talk about Speedb's Bloom filters. Pairing is caring. We have with us the presenter Niv Dayan, professor in Toronto University, and he specializes in data structures, and also Busmat Tuvel, our product manager. Um, and that's it. I think as today our topic is very technical, and I'll let Neve start, and let's go.
Okay, hi everyone. Thanks very much for having me. Thank you, Dan, for the introduction, and Busmat for being here and hosting me. So I'm Neve. I'm a professor at the University of Toronto, and I deal with data structures. I'm also involved with Speedb, and today I'm going to talk about a really cool technology that's been developed at Speedb. This is called paired Bloom filters. So this is an extension of the traditional Bloom filter data structure. And I want to emphasize this is a cool thing that was invented by two researchers at Speedb called Noam Haham and Yechiel Yochai. So this is not my work. I'm merely the presenter, but I'll be happy to present this and answer any questions at the end. Okay, so first of all, we will start from the ground up. So let's first of all talk about what is a Bloom filter, and then kind of motivate how we get to paired Bloom filters. So a Bloom filter is a compact probabilistic data structure that answers set membership queries. So it represents keys in a set, and it allows users to ask, does a given key exist? And in response to such a question, it can return a positive or a negative, indicating whether the key exists or not. Now, specifically, a Bloom filter cannot return false negatives, but it can return, it cannot return false negatives, but it cannot return true negatives, but can return false positives with a tunable probability that depends on the amount of memory that it has been assigned. So the common use case for Bloom filters or for filters in general in the context of databases is when you have a lot of data in storage and you want to quickly test whether a given key exists in the data set in storage. So the common use case is to place a Bloom filter at a higher layer of the memory hierarchy, say in memory, and then to just be able to access the Bloom filter in memory and say, okay, does a given key that I'm looking for exist? If the Bloom filter says no, I don't have to access storage to look for the key. So in this way, filters allow us to save storage accesses and network hops and thereby improve system performance substantially. Okay, a killer app for filters is log structured merge trees and LSM trees. And this is really kind of the bread and butter of what Speedb is doing as a company. I'm not going to describe LSM trees in detail. I'll just say that essentially, an LSM tree is just a series of sorted arrays that exist in storage. So a data item might inhabit one of these sorted arrays. And the way that Bloom filters help in this kind of application is we can attach one Bloom filter for each one of these sorted runs. These Bloom filters will be in memory. Then as we're querying the data structure, we can, before searching each one of these arrays in storage, we can check the filter for the existence of the key. If the filter returns a negative, this is perfect for performance because we skip doing an expensive storage access. And this is because storage tends to be much slower than memory. If the filter returns a false positive, this is not so good for performance. It forces us to access storage, not find the key we're looking for, and then terminate. Or if the filter returns a true positive, then we just find the key we're actually looking for, and the search can terminate. Okay, so that's the use case. All right, and of course, the more memory we allocate to these filters, the fewer false positives generally happen. And so we have this trade-off between memory and the false positive rate that we can play with here to strike different performance trade-offs. Okay, so now let's take a look at how Bloom filters actually work as a data structure, independently of LSM trees. So a Bloom filter is just a bitmap with k hash functions. And to insert a key into the Bloom filter, we just hash the key using the k hash function. So in this case, I'm using just two hash functions, so k is equal to 2. And we map the key using these random hash functions into to random bits in the bit vector and set the corresponding bits from 0s to 1s, or keep these bits set to 1s if they're already set to 1s. Okay, so in this way, we can insert many keys. Eventually, we can query for these keys, right? And to query a key, you again hash it using the same hash functions to k random bits, and you check whether all these bits are set to ones. And if at least one of these bits is set to 0, then you know for sure the key could not have been inserted. Because if it had been inserted, that bit would have been set to 1. So this allows you to return a negative, and you know that this is a true negative for sure. No false negatives can happen. On the other hand, if you're only finding ones for the corresponding bits of the key you're looking for, then it's likely that the key exists, but it could also be the case that other insertions of different keys cause those bits to be set to ones. And so this is how you can get a false positive. OK, so a natural question here is how many hash functions should we use for the Bloom filter? And OK, so in the extreme case, you can use one hash function. But that might be too little, because if you're only using one hash function, then every time that a query is hitting a 1, you're going to be returning a false positive. So you'll end up with a pretty high false positive rate. As you add more hash functions, the false positive rate drops because it becomes a less likely event that more and more hash functions for the same key will all map to ones. Okay, but this actually only happens up to an extent, because eventually, as you continue adding more and more hash functions for each key, for each insertion, more and more bits in the Bloom filter get set to ones, and that actually starts causing the false positive rate to deteriorate. And so there's actually an optimization space here with respect to the number of hash functions that you're using. You can measure the false positive rate with respect to the number of hash functions. And as you see, when we're using few hash functions, the false positive rate is high. As we increase the number of hash functions, it drops until it starts increasing again. So we can optimize the space, and actually there's an optimal number of hash functions. And the optimal number of hash functions turns out to actually be this formula. So this is a known result. It's natural log of 2 times m, where m is the number of bits per entry. Okay, so you can remember that, but I'm not going to derive it here. Now, assuming that the Bloom filter is using the optimal number of hash functions with respect to the amount of memory that it has been allocated, the false positive rate for the Bloom filter turns out to be 2 to the power of minus k, where k is the number of hash functions you're using. Okay, and then you can plot this false positive rate for different number of bits per entry to reason about the memory versus false positive rate trade-off. Okay, so now that we've done all of this, we can reason about the costs, the computational costs of inserting or querying the Bloom filter. Okay, so for an insert, you have to hash a key using k hash functions to k random bits. So the number of hash functions you have to compute is k. For a positive query, you have to check k random bits in the Bloom filter. So also, you have to check k random bits, the number of hash functions. Interestingly, for a negative query, the number of hash functions that you have to check is on average 2, because on average, because you can, so a negative query can terminate as soon as it finds a 0. As soon as you found the first 0, you know for sure the key doesn't exist, and so you can abort the query. And on average, a negative query finds a 0 after it looks at 2 random bits. Okay, so the average negative query cost is 2 hash functions computed. Okay, so now that we know these costs, we might ask, are these cost properties okay for the way in which modern hardware operates? And here the thing to observe is that, modern computers have a very deep memory hierarchy. So we have most of the data in DRAM chips, and then we have a whole CPU hierarchy of L3 to L1 caches. Finally, data gets into the CPU registers, and only then it can actually be operated on. And the point is that taking this movement of data from memory into the CPU registers can be quite expensive. So this, moving data from DRAM to the registers can take 100 to 150 CPU cycles on modern machines, and this can be quite slow. Okay, and the issue with respect to the traditional Bloom filter costs are that each one of, so each hash functions we compute might go to a different part of the Bloom filter and have to, read, a random and different hash function into the registers. And so basically for each one of the hash functions we compute, we'll have to incur one cache miss at a cost of approximately 100 to 150 CPU cycles. That turns out to be quite expensive. Okay, so that's where our problem starts off with. And there is a very nice solution to this problem called block Bloom filters. So this is still not Speedb's work. This is from a paper from 2010 called Cache, Hash, and Space-Efficient Bloom Filters from the Journal of Experimental Algorithms. And this paper tries to alleviate the problem of incurring too many cache misses for queries and insertions in Bloom filters. Okay, so what this paper proposes to do is that when we insert a key, rather than mapping it to k totally random bits within the Bloom filter, we can actually map each key to bits that are far closer to each other within the Bloom filter. So in fact, what we'll do is we'll make sure that each key gets mapped to only one cache line in the Bloom filter. And this means that for insertions and queries, we'll only ever incur at most one cache miss per operation. And the way we do that is we partition the Bloom filter into blocks. Each one of these blocks is the size of one cache line. Okay, and to insert a key, we're first of all going to hash that key into a random block within the overall Bloom filter. And once it's been hashed to a block, we're going to then insert that key using k random hash functions into that particular cache line, as though that cache line is an independent Bloom filter. Okay, and by so doing, every insertion or query will incur at most one cache miss. It only ever has to search one of these cache lines because all the hash functions for a given key have been localized to just one cache line. So this brings our cost for all the different operations to just one cache miss. Okay, so far the picture seems pretty rosy, but as is the case with computer science, whenever we do something, there's usually some trade-off, and there's a trade-off here too. So the side effect here is that block Bloom filters lead to an uneven distribution of entries across the different blocks or the different cache lines. So a different number of entries because might be hashed to each one of these blocks. Okay, so what you could do is actually draw this distribution. So you could draw the distribution of the number of entries that map to each one of these blocks. And we would observe that some of the blocks are going to be overflowing, meaning that they have too many entries, and some of the blocks will be underflowing, meaning too few entries are being mapped to them. Okay, so it turns out that this actually impacts the false positive rate for the Bloom filter. So what you can do is you can plot the false positive rate for the filter with respect to the number of entries that have been mapped to a particular block. So here I'm actually plotting the false positive rate for an individual block with respect to the number of entries that have been mapped to it. And interestingly, what we observe here is that overflowing blocks tend to increase the false positive rate more than underflowing blocks decrease the false positive rate. Okay, so it is true that while blocks that have been mapped too few entries will have a lower false positive rate, but blocks that have been mapped more entries will have a disproportionately higher impact on the false positive rate. These things don't actually balance each other out. The impact of the overflowing buckets is higher. And overall, this implies that your overall false positive rate significantly deteriorates relative to a regular Bloom filter. Okay, so this picture really captures the problem with blocked filters. What it shows you is that, as we increase the number of bits per entry for the filter, a Bloom filter maintains a reasonable false positive rate, but block Bloom filters, because of the uneven distribution of entries across the different blocks, their false positive rate doesn't scale as well. And the reason is that the overflowing buckets really kind of damage your false positive rate. Okay. So to address this problem, at Speedb, we have created paired Bloom filters. And they precisely address the problem of how to better scale the false positive rate while maintaining the good performance properties of block Bloom filters. So in a way, paired Bloom filters try to achieve the best of both worlds. They're trying to get the false positive rate of a regular Bloom filter, but they're trying to achieve the performance properties of block Bloom filters. Okay, so, and here is roughly how they work. So, okay, this has been developed in Speedb over the past few years. Okay, so if we start off with a regular Bloom filter here, what we're going to start off by doing is, first of all, partition the Bloom filter into batches. Okay, and each batch is going to be quite large. A batch is larger, much larger than a cache line. And I'll tell you exactly why we divided into batches later. I'm not going to that now. I'm just telling you we're doing it. Now, after we divide it into batches, we divide each batch into multiple blocks, okay, as we did before. And each of these blocks is the size of one cache line. Okay, so to insert a key, we're first of all going to hash it to a random block within one random batch, okay, as we did before, actually. And then once it's been mapped to a block, we're going to, again, insert it using the k random hash functions to k random bits within that specific block. Okay, again, as before, this is going to lead to an uneven distribution of entries across the different blocks. Okay, so now I'll show you how to fix this uneven distribution. So what we're now going to do is build a histogram that tells you how many entries have been mapped to each one of those blocks. Okay, so the number here above each one of the buckets, of the blocks, tells you how many entries have been mapped to them. Okay, now that the histogram is built, what we can do is we can conceptually pair the most underflowing buckets with the most overflowing buckets or blocks in each one of the batches. Okay, so 3 is going to pair with 7 because 3 is the most underflowing and 7 is the most overflowing. And here, actually I should have actually paired 6 and 4 because this is the most overflowing and this is the most underflowing. Okay, but the point is that we continue to do this pairing until all the different blocks are paired. So we continue to pair the most underflowing with the most overflowing until everything is paired in each one of the batches. Okay, and what this does is it effectively equalizes the number of keys that map to each pair of blocks. Okay, so given that these two pair with each other, right? Conceptually, it's like we can move entries conceptually from the overflowing blocks to the underflowing blocks. Okay, now specifically, what we actually do is for all the entries that map to a particular pair of blocks, we actually use a half of their hash function. So for each one of these keys that map to this pair, for each of these keys, we're going to use half of its k functions to map it to one of the blocks, and the other k hash functions to map it to the other block. Okay, and by so doing, we evenly distribute the hash functions for all the keys across these pair of blocks. And this causes essentially the number of ones in each one of the blocks across the whole filter to become equalized. Okay, so this allows us to address, to precisely address that uneven distribution of entries that we've seen before. Okay, so so now in addition to this design, we make sure that in each block we also encode the ID of the pair that has been mapped to it. Right. So the beginning of each block here is going to begin with an ID, and that ID, right? That ID just corresponds to the pair, and we use that during queries, and I'll show you how in a second. But here's how a query works. A query is going to start off by looking at one of the blocks in the pair. If it finds a 0 for one of the entries in the pair, it's going to terminate. It does not need to go to the next block in this case because we've already found a 0 and we know that the key doesn't exist. On the other hand, if all bits that it found in one of the blocks, if all of them are set to ones, then it can follow the ID to the paired block, and then it can continue the query in the paired block. Okay? So essentially, a query completes after at most 2 cache misses, right? For the two blocks in the pair. Okay. Now overall, you can do a cost analysis of the average number of cache lines and of the cache misses that you incur for each one of these operations. Now, an insertion is going to insert every key into at most 2 different blocks, so it's going to incur at most 2 cache lines. A positive query is going to find ones across all the bits that a key corresponds to, so it's going to have to visit both cache lines in a pair. But interestingly, a negative query is going to incur a much lower number of cache misses. It's going to incur 1 plus square root. It turns out that I'm not going to analyze this, but a negative query incurs very close to 1 cache misses. And this thing, this expression that we add to it, is just the probability that we find all ones in the first block and have to continue traveling to the second block. So this expression turns out to be very close to 1. I'm not going to analyze it in this presentation, but the point is in many applications, what we actually care about optimizing is negative queries. And the reason is that for a positive query, we have to usually do a storage access afterwards anyways. So that completely masks the cost of accessing the filter. What we really care about is negative queries, because a negative query, after a negative query, you just abort the query. And so we want to be able to abort the query as quickly as possible. So these blocked Bloom filters have the nice property that the number of cache misses that you incur for a negative query is very, very close to 1. Okay, so now another concern that people looking at this presentation might have is that these IDs can take up space, right? So at each block, we have an ID that requires you to identify the paired block. Sorry, I have some noise here. I'm going to close my window. Okay. So these IDs take up space. And a concern would be that they might take space from the bits in the filter that I actually use to do the filtering. Okay, so we might want to reason about how much space that actually entails. And it turns out that the amount of space that you need to encode one of these IDs is just log base 2 of the size of a batch, right? Because we only ever do the pairing within a unit of a batch. Okay, and in this construction, we set the batch size to be 128. So, the batch size is 128 blocks, and only within that unit we do the pairing. And so because of this batching, you need at most 7 bits per block to be able to identify the pair. Okay, so given that a cache line is typically 112 or so bits per entry, using 7 bits out of 112 is not that much of an overhead. And because of that, right, the overhead of these IDs is very, very negligible and doesn't affect you too much in reality. Okay, so this is actually the last slide of the presentation, but this slide really kind of captures the main takeaway. And the takeaway is that with paired Bloom filters, as you increase the number of bits per entry, you see that paired Bloom filters are able to really approximately match the classical Bloom filter with respect to the false positive rate, and significantly improve upon block Bloom filters. At the same time, paired Bloom filters provide performance characteristics, especially for negative queries, that are very, very close to those of block Bloom filters. So in this way, they allow you to achieve really the best of both worlds. Okay, and that's the end of my presentation. I took significantly less time than I expected, and that leaves a lot of time for questions if there are any.
Thank you, Niv, for a super interesting session. Just want to mention before the question is that the paired Bloom filter is available on our GitHub repo. Of course, it's open source, so you can use it, you can try it and let us know. Also, in the documentation in our Git book, we have some benchmarks that compares between the paired Bloom filter and the blocked Bloom filter. So feel free to take a look. You can get more info there. Let's see if we have some questions from the audience.
I see Cole wrote us. This reminds me of the first assignment in course from Stanford.
We'll look at that. Thanks for the reference. I'm not sure what that link refers to, but I'll check that out after.
And we have another question from a LinkedIn user. Does this strategy work in systems where filters are updated frequently?
Yeah, completely. Okay, so perhaps what I'll do is I'll talk about the applications within LSM trees. So Bloom filters are widely used in LSM trees, and these paired Bloom filters have been engineered to work in the context of LSM trees. In an LSM tree, I talked about how LSM trees consist of these sorted runs in sorted arrays in storage. Every time that we merge two of these runs that belong to the LS entry, we actually rebuild a Bloom filter from them from scratch. And that's, so I should say a Bloom filter is actually an immutable structure. No Bloom filter that exists actually supports dynamic data, updates or deletes. So in the context of LS entries, for any Bloom filter, what we do is we recreate the Bloom filter from scratch whenever we compact different parts of the LS entry. And in that process, right, we build a new Bloom filter. So in this case, we build a new paired Bloom filter. And we do that at no significant additional overhead relative to traditional Bloom filters. So in this way, this does allow us to support dynamic data, right, in the context of LS entry-based storage engines. Thank you for the question.
We have another question from, let me show you. This idea also reminds me of a concept of the modular Bloom filter, coupled with the bulk Bloom filters. The cache misses analysis that you did is very interesting, by the way. You can all read this. The idea of pairing modular with block Bloom filters is awesome. Thank you, Manu.
Thanks, Manos. Manos, nice to see you here. Okay, thanks very much for the reference. I mean, I'm not familiar with this work. No, actually, okay, interesting. So I see this is one of your work. So, okay, so we'll check that out afterwards. But thank you very much for this reference.
Cool. Guys, if nobody else has any more questions, obviously this video is available on our LinkedIn page, on YouTube, Twitter. You are welcome to join our Discord. You have the link. And if you have any other ideas for other webinars, please send us. We're happy to get more ideas. Thank you, Niv and Busman, and have a great weekend.
Bye-bye, everybody. Thank you.
Bye.